Ну, правда, я не знаю, никого нет. Что в таких случаях делать? Ну, вообще надо перестать записывать, на самом деле это зло, я считаю. Как бы, ну, все сводится к просмотру каких-то фильмов. Зачем? Может быть, просто взять и прекратить запись, а?
Почему?
Не, ну просто потому что народ не ходит, а так будет ходить. Вообще, 10 часов это, конечно, очень сложно. Но для меня тоже сложно.
Как показывает практика, там, прекращение записи редко это исправляется.
Ну ладно. Так, хорошо. Тогда будем двигаться. Хорошо. Значит, ну а я хочу прям начать, на самом деле, so I need to speak English. So I want to start with a new theme, which is Riemannian manifolds. So I just start with definition. Well, again, Riemannian manifold is a smooth manifold, so let X be a smooth manifold. And then a Riemannian metric G is a smooth, well, on X, is a smooth section of what, of S2 T star X. So symmetric square of cotangent bundle such that for any X which is a point in my manifold, if I take G and consider it at my point X, right, this will be S2 T star Px, and this gives these positive, so positive definite quadratic form, bilinear form on Tx, on Txx. And then if I have X, I have such a G, then a pair X and such G is called Riemannian manifold. It's called a Riemannian manifold. So we have we introduced new structure, which is G, which is this symmetric tensor, which gives me at each point positive definite form at my tangent space. All right. And then why this thing is good? Well, for example, there's a way to measure length of a curve if I have such thing. So it's another definition. So I just define what is the length of a curve. So let gamma is from closed interval to X. So this is a smooth curve on X. Then define and I will denote it as L of gamma. As follows. So I just, it's an integral, obviously, from A to B. But then I need to use my remaining structure, which is, so I need to do it like that. So I take G, then I put, consider the point gamma of T, and then compute its value at gamma prime of T, gamma prime of T. And then I take square root of this, because I can, because it's positive definite, right? And then, well, I integrate with respect to T. So this is definition. Well, it's clear how this, what's the motivation of this formula, right? So let's just spell it out real quick. Or rather, motivation, or I don't know, an example of this. So if I have just x is Rn, and I have just usual 2 points, right? So I have x with coordinates xn in Rn. I have y, which has coordinates y1, yn. It's another point in Rn. So how do I compute the distance between y and x? Right. So I take clearly x I minus xj, yi minus xj squared, right? And then I take a sum of this over I, and then take a square root, right? So, and then, well, I need to, so this is like a curve which is just straight line, right?
What difference is this? What? Xj and...
Sorry, it's both should be I, of course, yes. This is I. Just usual scalar dot product on Rn, right? So that's how you compute and distance between 2 points, and then of course if you have like a curve in Rn, right? So if you have the curve in Rn, then it also can compute the distance of it using this formula, right? So you kind of break it into small pieces, right, and compute the length of each piece. Like in this piece, this is just a straight line, and so that's how it's taught in kindergarten, right? So you have to differentiate d gamma over dt squared. So the length of the small pieces is like that, plus d gamma 2 of t squared plus and so on t gamma n of dt squared. So then I take square root, right? Take this. And so therefore this formula can be generalized. So I just consider G on Rn, which is at each point is just dot product. Okay, and okay, this is positive definite form. So I can replace it with any G, and of course then this will be such a formula. Right, so that's clear that this is 2, and this is 1, and 2 is generalization of 1. All right. Now let us relate this to our previous material, which is connections in geodesics and so on. So actually there is a very good choice of connection if I have a Riemannian manifold, which is called Levy-Schwitt connection. So we have the following statement, proposition. So that X G be a Riemannian manifold, and then, well, there exists unique connection nabla on X satisfying the following properties. First, nabla has no torsion. So nabla has no torsion, which is the same as saying that nabla Vi, well, nabla, what, VW minus nabla WV equals to the commutator of VMW for any two vector fields on X. The second condition is that that G is invariant with respect to covariant differentiation. So shorthand writing of this is this. So G is constant in a way, but what does it mean? Because G belongs to S2 T star X, right? And nabla can eat well, elements of Tx, well, sections of Tx, right? So, well, sorry, this should be gamma of this, right? So it's a section of this, right? And so nabla can eat sections of Tx. So what does that mean? Well, we know that, so we kind of abuse notation and you know, we discussed, I think, on the seminar. So if I have nabla, then on some vector, so connection on some vector bundle E, then there exists some nabla star on E star, right? And so we abuse notation and write nabla and nabla star, like nabla for nabla star, right? Just assuming that it's the same. So this gives me way to apply nabla to T star X, right? But also how I can, you know, extend it to any tensor of T star X, in particular symmetric one, just by the following rule, by Leibniz rule. So nabla of S1 tensor S2 is just nabla S1 tensor S2 plus plus S1 tensor nabla of S2. That's just definition. So therefore, indeed, this makes sense now to write like this after we discussed it. And so this is like a condition. We will see in more details what this means, right? Because we need to prove this proposition. All right, so first of all, let me give a definition that this nabla from proposition is called the Levi-Civita is it 2T or yes connection. Okay, so let's prove the proposition. Proof of proposition. All right. So I take my G and let me just expand it. So any tensor, well, any element like this, right, can be written as a sum of this sort. G, what would be my notation? 1I tensor G 2I and sum over I. All right. So we'll just write. Then, well, I know that if I take nabla of G, say 1I, and then evaluate it at a vector field V, this is just by definition of nabla on E star, which is T star X, just gives me dg1I of V, right? Yes. Minus. So here I mean dg. So like this, right?
And GI there are sections on T star X, right?
Yes.
Okay.
Yes. So these are sections on T star X.
Right.
Yeah. So I'm kind of recalling the definition of
Yeah.
nabla star.
Yes.
Right, and it was what was like that, minus G1I, and this is for any I, and I can replace 1 with 2 here, or with any actually section of T star X, indeed. So, but just as an example, just as a recall of what is nabla star is, I need G1I of nabla V. All right, and then I can, now I can use this and this together. This will give me what? So I just explained in more details what this means. So sum over I. dg1I. So, of course, I will not write this square brackets once we understand that dx on the whole thing is a function, right? dg1 of v, right? Tensor G2 of W minus G1I of nabla of V, right? Tensor G2I, should be, yes, should be like that, it's all good. Maybe before this term, let me So before this term, sorry, I'm a little bit rushing it. Right? So, so I have what G by Leibniz rule. I also need to act by D in here, right? So G1IV tensor D G2 IW, and then minus G1I nabla V tensor G2 IW. And another term, so minus G1I V tensor G2I nabla applied to W. So sum over all this is 0. Okay, so that's just the same thing as this one, I claim. Okay, once I use this. On the other hand, I'm claiming that what's written here is that dg v1 vw. So I'm rewriting this as follows: dg vw equals. So dg vw is actually this thing. So if I sum over I and take this, so this is like really Leibniz rule, equals G of nabla, and then okay, so this is a form, right? I want to make it a function, so I want to apply it to some vector field, third vector field. So I have 3 vector fields, V, W, and Z. So let me apply this to Z. Right? So I'm claiming that this is just so this is a form, right? And it's Z. So like this is a function. This is a form. So I will have. So basically, what's written here is this guy. If I substitute Z in here and here, and this guy, I should substitute Z as a subscript into nablas. Okay.
Is that vector control?
Yes. Mm-hmm. And this will give me G of nabla. Sorry, I have to switch to Z. I don't know why I start saying Z. I'm kind of more used to Z. So nabla Z V W plus G of V nabla Z W. So we have such a thing. Any objections? So basically, what I'm saying is that this term is this guy because like dx by Leibniz rule, right? I act on it. So this is one form evaluated at a vector field Z. So this Z goes. This means that this is one form evaluated Z and this one form evaluated Z. And on this side, what should I evaluate? So this nabla has like an open argument where I should put Z.
Слева должен быть тоже набла, да, не D?
Нет, слева вообще никакой набла нет.
Слева D, да?
Да. Вот прямо, вот это слагаем. Никакой наблы здесь нет. Okay. So now this is the same as this. Actually, we can go backwards. So this is just really what 2 means. If I do all this work, now actually, what does it mean to take dg vw and relate it to z? It means that I take vector field z and apply to function gvw, right? That's just what is the differential of a function, right? So this is taking vector field, which is differentiation, and apply it to gvw. That's what's written on the left. On the right I have this guy, but also I would like to switch w and z here and use no torsion property. So I will have g nabla z w plus g v nabla w z. Sorry, v here. And plus g v. So since I switched, I need to write commutator of w and z. Because I have no torsion. So I can switch these two. This guy is bilinear. I'm switching, and so therefore I should add commutator because I have this property. Now what I do, so I'm having nabla zv, nabla wz, and I would like to write 2 more such expressions with so I will have system of 3 equations, star, and then I do cyclic permutation. In star I take z to v, v to w, and w to z. So I just do a cyclic permutation of vector fields, right? And write the same expression. This will give me another equation. And actually I do this 2 times. So I have 3 equations, and I will have actually 3 unknowns. Right? Actually, I'm trying to solve for nabla of one field to another, because I'm trying to find, so G is given to me, right? So I'm trying to find connection, which is by these properties, right? So I will have, so this will be like a system of 3 equations, and my unknowns are, nabla v z, nabla zw, and nabla wv. All right, so 3 equations. And these are unknowns. And this is like really a linear, really it's a linear system of equations for 3 unknowns. Because G is linear in both arguments. And so how to solve it? Well, I just eliminate 2 of them. Say I eliminate nabla vz and nabla wv. And then I will have the following expression. Well, you can believe me, or you just can do it in your head. well, after I give you example, answer, it will be clear that it should be like that. Or at least what linear combination of these three equations you need to consider. So we'll have the following relation. 2g of v nabla zw equals to z applied to g, gvw minus v applied to g wz plus, and then plus all cyclic permutations, well, with signs. So plus what? W G, sorry, I keep writing this. G Z V, right? Minus, okay, so maybe it's not the best order to write the terms, but it's clear. So, no, it's okay. So terms of this kind, but this one goes with minus, and then terms of the following kind with commutators. G, Z, V, W, and then minus G, V, W, Z, and then plus the last term G, W, Z, V. So what I need to do, I take the first one, subtract the second one, and then add the third one, and express the term with nabla zw. Then what I get is this, clear. Actually we are done because G is non-degenerate, right? So therefore this defines nabla zw, right? So G is non-degenerate. So therefore this, I don't know, double star defines uniqueness. In our proposition.
And the first term is 2, not z, right? The very first term.
It's z,
Not 2.
not 2.
Got it.
Yes. Well, this 2, because this term will be in this, well, in the first one and third
Yeah, it
one.
makes sense.
Yeah.
Just,
No, this is it. Yeah. Okay. So this is, I guess, not defines, what should I say? Implies. Sorry. Implies uniqueness. Right? On the other hand, you can go backwards. You can say, okay, suppose that I define nabla using this equation, right? Then, well, I need to check that it is really a connection. And then I need to check that it has no torsion really, and then, you know, going back through all these computations, they're all reversible. You can prove that it's invariant. Okay, so this is some just explicit computations, but the main idea is that you have such a relation which defines number z of w for unit.
Надо просто вроде в обратную сторону можно пройти.
Ну да, да. Да, ну как бы получится, что у вас есть, если вы ее определили, то у вас есть, чтобы в обратную сторону пройти, вам нужно все равно без кручения, чтобы она была. То есть это надо проверить. То есть мы на каком-то этапе воспользовались, что она была без кручения. Да. Хорошо. Okay, so let's assume that we proved the proposition. Okay, so now let me recall the exponential map, because the next theorem will actually involve exponential map. So recall. So exponential map is from where to where. So x is from a neighborhood n0. So this is inside t px, right? P is some point. So neighborhood of 0 inside tpx. Right, so 0 is inside here. 2 x. And so how what is the construction? So you take v, and then you take unique geodesic such that at its tangent vector to 0. So okay, let me gamma v, and you map it to gamma v of 1, where gamma v of t is first of all its geodesic. Also gamma v of 0 is p, so such that, and gamma prime v of 0 is well, v. So that was the construction, and we say that okay, n0 is some neighborhood of tpx such that actually gamma v of t can be evaluated at 1. So there is some neighborhood like this. Well, we didn't prove it, but okay, just I left it for a seminar. But you just really need to closely to geodesic equation to prove that. All right, so now that's one thing. Another thing which I also didn't prove, just to accelerate, is that I can shrink n0 and make it what's called normal. So if n0 is small enough, then x is differ to the image. So if n0 is this small, so that exponential is diffeomorphism, then such n0 let us call normal. Such n0 are called normal neighborhoods. Okay, so that's some information about exponential map that we need. All right, so now let us use that and combine it with remaining structure on G. So proposition or theorem, let xg be a remaining manifold So basically it says that geodesics locally minimize the length of a curve. It's a very important result. So namely, so let me fix P in X and let me consider N0 inside TPX and such that N0 is normal, first of all, and also it's an open ball. So on TPX there is a metric, right? So I know what is a ball there, right? What is like what is sphere, what is a ball? An open ball, I want N0 to be open ball first of all, and also normal, meaning that exponential map is diffuse. All right. Also, let me denote NP to be exponential, like the image of N0. Just the definition. And also another notation for any Q from NP, let gamma PQ gamma PQ, it is a curve from 0 to 1 to NP. It's a unique, so let this be unique geodesic such that gamma of 0, gamma PQ of 0 is P, and gamma PQ of 1 is Q. So such geodesic is unique. So I can find such geodesic, and it is unique because I want my N0 to be normal. Normal means that exponential map is diffuse. In particular, it means that this is injective. So therefore, such geodesic is unique. All right. This is my initial setup, and then I am saying that then for any other curve, gamma 0, 1 to x. So you see, here I don't even require to belong to NP. It can go outside and then go back. So such that gamma of 0 is P, gamma of 1 is Q. We have L of gamma is greater than L of gamma PQ.
Просто мы понимаем, почему она единственная. Гамма при Q.
Ну, вот я уже попытался сказать, она единственная, потому что N0 это нормальная окрестность. А нормальная окрестность это значит, что экспонент дифферморфизм, в частности, вот это инъективное отображение.
У нас
Если бы там было две,
да, понятно.
то тогда бы мы...
Нет,
Ну, просто бы они начинали с двух разных векторов. Вот, как бы такая картинка была.
ну, там не негативно просто уже было.
Да, это P. Вот.
Да, хорошо.
Получается, два разных вектора дают...
Если даже не важно, что два разных вектора, если они просто, если две, ну, если они в точке Q совпали, то они везде совпали.
Ну да, нет, вот просто я говорю, что могло бы случиться так, и тогда бы просто экспонента была бы... В принципе, такое может случиться за пределами.
Да, это понятно.
Вот. А я говорю, что она достаточно маленькая, что такое не случается. Но, в принципе, можно было бы подумать, что вот такое что-то как бы вот происходит тоже. То есть один и тот же вектор, они как-то раздваиваются и опять сходятся, например. Но такого тоже не бывает, как мы доказали еще на прошлой лекции.
Нет,
Что
да.
если у меня вектор задан, то геодезическая максимальная, она одна единственная.
Но у нас это все равно не важно, потому что, ну ладно.
Ну как, все равно, как бы, группы две...
Ну да. Но у нас
Ну, может быть, у них разные длины, я не знаю. Это сложно.
Нет, я имею в виду, что он с дифферморфизмом, и что он биективный автоматически.
Ну, он объективный, да.
Вот, ну ладно.
Нет, ну тут как бы вектор один и точка одна.
Да. Угу.
А геодезических две. То есть объективно здесь все равно не спасает. Но я говорю, что вот этот мы
я
исключили.
понял. Угу.
Вот.
Да, такого не было. Хорошо.
Okay. So, is statement clear? So basically we say what? Okay, let's take P, let's take Q inside N0, and there is a geodesic. And then if you take any other curve, it can go outside even. It doesn't really matter. Then the length of this curve and will be greater than the length of geodesic. But this is only local. I can only say this for Q inside zero. Some global statements we will not get to them because this will be like we'll need the whole separate course. But like in particular for compact remaining manifolds, you can go to global version of this, but not for any. Right. Okay, so let's prove this, but first, okay, so the proof will take us the whole time of this lecture. Maybe I'll take some of seminar time, because, well, but the main idea is the following. What will be going on? Use what's called spherical coordinates around P. Basically what it means that, well, I will say in a, yes, okay, so maybe let me say right now, so what it means. So, namely, let S be unit sphere just in Rn, where n is dimension of X. And let me pick delta. This is just a positive number. Is such that, well, we have map, just a really stupid map, but let us call it somehow. So this is a map from the direct product of this open interval S times S to n0 without 0, right? And this is just I take t from here, v from S, right, and map it to tv. Is a diffeomorphism. Well, basically, it just says that delta is radius of n0. That's what it says. And then I'm taking unit sphere, and then also another coordinate which goes along the radius, right? And that's how I parameterize n0 without 0. And then, well, of course, I can take these are coordinates on n0 without 0, but I can also make them coordinates on x without on the image of n0 without 0 using an exponential map. So we define phi is just a composition of exponential map and rho. And what we will need to, so we are going to work with length. Length is given by g, which is a section of something. So we need to compute actually this g in spherical coordinates. The idea is compute g in spherical coordinates. And we actually would like to see that, so we want this is like some not rigorous statement to see that like phi star of g is, well, has no cross terms. Meaning that phi star of g, well, it will be something like dt squared, where t is a coordinate in here, plus some omega, it will be like omega bar squared, where omega is of one form on well, it's really one form on S. So basically, if I'm using coordinates, right, and I'm trying to write some expression of some form, well, this is not a form really. This is like a symmetric tensor, right? Yeah, and this square means it's just, symmetric square. I'm kind of abusing notation here. Then what it will be? It will be like some squares, right, of variables, and also cross terms. Something which will depend on dt, and also maybe some coordinates like d phi, where phi is a coordinate on S, right? So our main concern is to prove that in phi star g there are no such things. Why? Because our geodesic in these coordinates will look like the following thing. It will start from 0, from P, and go along the radius. Okay? So if I go along geodesic, only this term will give me something non-zero. Because I'm not going from side to side. But if I'm taking some other curve, So I'm going this distance anyways, but also I'm changing angle a little bit and so therefore, if I'm taking some other curve, this will give me some non-zero term in my length. So the idea is that in geodesic only this term works. In any other terms, this also starts working, and so therefore that's why my length actually will be bigger. And both of them are positive, right?
And
So
some cross terms,
yeah, this will screw up the argument.
Yeah, makes sense.
Okay. So let us do this. Right. So first of all, let me introduce some orthonormal bases in TPX. I'll denote it by psi1, psi-n. So this is in TPX. Or to normal basis. Meaning that if I take G related to P and related to psi I, psi j, so that is just delta ij. And then let me take a dual basis to this. So let omega, so define omega I, so these are really one forms. So therefore these are sections of T star X. And I here again runs from 1 to n. So at P, this is just dual basis to psi's, right? So omega I, so defined by at P, and related at psi j is just delta ij. Again. But at any other points, I will just I will just use parallel translation to go from point P. Okay, so omega I Q, no, let me use the same notation, of V is just omega I P of tau 1 inverse of V, where tau T is parallel translation with respect to gamma PQ. So I'm defining omega i's as a dual basis at point P, and then any other value at any Q from, so this is for any Q from P. I define using parallel translation. Okay. Then okay, so I'm claiming that actually G is sum over omega I squared on n p. I from 1 to 1, 1 to n. So this is definitely true at point P because of this. But then in all other points it's true because G is invariant with respect to the connection. So this is parallel translation with respect to gamma. Gamma is a geodesic, and geodesic with respect to what connection? We also only had the Riemannian structure, right? So I need to say that this is a Levi-Civita connection, right? So, and since it's Levi-Civita connection, G is invariant actually with respect to parallel translation. So it's invariant with respect to, of course, covariant derivative, but more globally it's invariant with respect to parallel translation. So therefore, if this happens at point P, then it happens at any point U of NP.
Это очевидно, что такая форма гладкая? Или это вы думаете, наблюдать?
Такая форма гладкая. Ну, надо сказать, что у меня параллельно сдвиг дает мне гладкий вектор, правильно?
Там что-то типа того, что у нас в каждом направлении гладко, потому что параллельно перенос значит гладко просто в покрытии.
Ну да. Ну, сейчас у нас этот экспоненциальное отображение, дифеоморфизм, поэтому вот можно так сказать. Ну почему мы вообще... Нет, ну правильно, нет, значит, ну хорошо, я начинаю влезать в глубину вашего вопроса. Ну то есть связано с тем, что у меня есть вот эта теорема, которая говорит, что у меня решение дифференциального уравнения геодезического гладко зависит от начальных условий. Вот как бы вся соль вот в этом сидит. И гладкость берется вот оттуда. Поэтому вообще можно брать там дифференциал, там всякое такое от экспонента. Okay, so let's continue. So now I need actually to compute phi star of omega I. Okay, so this is one form, right? So it's one form actually on n0 minus 0 without 0, right? So I can actually write this down as fi dt plus some form omega I bar. Where so I need to write like this for some fi. So this is a smooth function in here, 0 delta times s, and so this is fi. And omega I, it's a smooth section of t star s, but its value, so it's a section on t star s, so therefore like but it also depends on a point, so sorry, on a point I should say like this, 0 delta times s. Okay. So basically it's a one form, but for any fixed point t, this is like one form on t on s, right? But it's kind of function on t with a value at one form. The important thing is that omega I, right? It is a form in here. If I write it down in coordinates, then like it will only have d of coordinates which run over s. That's what I mean.
З вами більше що тут просто побек форма з сфери.
Ну да, да. So what I'm saying is that yes, so here is no tensor with zero delta, so no part here. So all right, this is one thing. So I claim we can compute what are fi's, what are these functions. So fi, it take values in 0 delta times s, so it's a pair t, and then on s, I can expand any vector on s in terms of xi j, aj xi j, j from 1 to n. Sum of squares of aj is 1 because this guy is on a sphere. All right. So I claim that this is just ai. So it takes this and gives me the value is ai. Let's see that. Right. So this left-hand side, fi of t of sum over j, aj, xi j, it's the same as phi star of omega I, right? This omega I, evaluated at d over dt. Well, at what point? At point, well, this point, right? T sum over aj xi j. Right, so this one form, I put it on, at some point, it will become like an element of T star, this point of this guy, and then I can evaluate it at this vector. Well, it's clear, right? To get fi, I need to, evaluate it at d over dt. This omega I of d over dt is 0, right? This is what it actually says. And the dt of d over dt is just 1. So what you get is fi. All right. But at this point, we just need to recall what is a pullback and what is phi. So I'm claiming that if you go through all these definitions, it will be omega I evaluated at phi of this, which is just exponential of t sum over a j xi j, right? Omega at this point, evaluated at d phi of d over dt. And this d is at point tv, where v is this is v actually. All right. So I'm just expanding what is a pullback, right? And this is just phi of this point. This is just this thing. And then I need to apply d phi to this guy. All right. Next. Next thing is that I need to see that d at the point tv of phi of d over dt. Well, I need to recall again. What is phi? It's I need to take d over dt of exponential of t of sum over a j psi j. And take t, well, just like that. T is not fixed, so at point t, it's like that. Right, phi actually, so what is phi? Phi actually takes this point, TAV, and consider exponential of TV, right? So I take exponential and then I take differential, but differential related to d over dt is just differentiation of this with respect to value dt, right? Okay, but then actually what? So let me continue. So this guy is actually in our definition. So if this is V, right, then this guy is gamma prime V of t. Right, this is geodesic with tangent vector at 0 V, and it's derivative of this geodesic tangent vector at each point V. Okay, so I'm just continuing. So like at this, so this equals to Vi, so omega I at the point gamma V t gamma V prime of t. Like this. But then I remember the definition of omega I. It was given by parallel translation along geodesic. So actually this is the same as omega I at gamma VF of 0. So I can go back along geodesic by parallel translation to P, right? Which is, this is P. Of gamma V prime of 0. Geodesic is geodesic, so this is parallel, this is tau inverse of 1 of this guy. All right. So this is, but gamma V of prime of 0 is just V. Right, so this is actually omega I at point P of sum of V, which is sum over A j psi j. But now omegas are dual to psi, so this is actually AI.
То есть как мы делаем переход от Т к нулю?
А я вспомнил, что у меня омега определялась вот так.
А, да.
Вот. Ну и просто она определяется, это просто по определению, что вот это по определению то же самое, что вот это. Потому что гамма это геодезическое. Все, значит, окей, claim 1 is done. Okay, now claim 2. Okay, before claim 2, I think we need to have a break, right? Then we'll continue. So maybe let me write down the claim 2, which is what I announced. Is that sum over I from 1 to n fi omega I, which is cross terms, is 0. And что прыгаем. Если кому интересно, здесь я исследую книжки Пелгасона. Называется Differential Geometry или Groups.
Сейчас книжки можно еще раз?
А по-моему, она есть в списке литературы, я пытался, но вот Сигурд Дурф, Пелгасон, вообще классная книжка, он хорошо все пишет. Но понятно, я не иду по всем деталям, он там как бы во многих главах получает то, что как бы некие результаты, которыми потом пользуются. Вот я их по ходу вывожу. Значит, ну, как-то начинается с Differential Geometry, ну там Lie Groups, Symmetric Spaces, ну, еще что-то.